Among others, one can highlight the model of topological quantum computing, which was originally proposed by Kitaev. In 1997, he proposed using the topological states of quasi-particles for quantum computing. The main advantage of this computation model is that it is more robust to computational errors. In conventional models of quantum computers, it is necessary to additionally construct correction codes that will save the computational process from errors. In quantum topological computers, such a process is already built there at the model level. The idea behind quantum topological computing is pretty simple. It is based on the topological properties of space. Surely each of you has heard that from a topological point of view, a circle and a donut are indistinguishable. One object can be transformed into another. Also, in topological computations, no matter how computational errors distort the states, each topologically will be preserved. This means that we will be able to understand how it was originally before the error occurred. With this analogy, we can discuss the computational model in a little more detail. To implement computation in this model, quasi-particles called anyons are used. Such particles live in two-dimensional quantum systems. This leads to the fact that their statistics are more general than the usual Bose-on-Fermi statistics. When two such anyons are interchanged, their common wave function acquires a phase factor that can vary from 0 to pi. Recall that when bosons are interchanged, their wave function does not change, and when fermions are interchanged, their wave function acquires a phase factor equal to pi. Due to the presence of a non-trivial factor in the permutation of anyons, the process of quantum computation in a topological model resembles the process of knitting. At the first stage, anyons are prepared in the initial states, after which they begin to change places for each other. As a result of such interlacing, topologically distinguishable quantum states of the system are obtained. Moreover, the number of such states will depend on which anyons we used. For example, if we use particles that, when interchanged, give the phase equal to pi over 4, then 2n such particles have 2 to the n-1 power of topologically distinguishable states. If we interlaced n electrons, we will see that interlacing turns out to be topologically the same. Whereas topologically distinguishable states are the states for quantum computing. Moreover, in such a model, error resistance is intuitively understandable. No matter how we ruffle the woven fabric, its will still be preserved. That is to say, errors do not change the results topologically. This computing model is fully equivalent to the standard quantum computing circuit model in terms of its computational power. It can also be used to solve problems from the BPQ class in polynomial time. The universality of a model, as well as its fault tolerance to errors, mean that scientists from around the world are actively exploring this model. Currently, an active search is underway for a physical system on which this type of computation can be experimentally implemented. Here I will provide only a couple of references to contemporary works.